basically covered all the teaching we need for this topic. Obviously, what we now need to be able to do is to practice. And the really important thing now is to be able to practice with everything mixed up, all the different stuff that we've learned, okay? So I'm going to summarize all the formulae we've got, all right? And for now, I'm just going to focus on arithmetic and geometric sequences and series. And this little table helps us to decide which formula we're going to use. What type of sequence are we dealing with? Arithmetic or geometric, and are we after a sum or a term? Okay, and that helps us decide which of these formulae we're going to use. Don't forget our quadratic sequence, and the only formula we get given there is that one, an squared plus bn plus c. Not all that helpful. We need to remember some other formulas as well, but we will get to that as we go through. Right, really, it's just about practice, practice, and more practice. Okay, so let's dive straight in. We're going to look, all of these questions actually come out of matric past papers. So let's dive straight into this first one. And what it's asking us to find the 8th term of a sequence about which we know this and this. We also know that it's an arithmetic sequence. So the first thing I'd be asking myself here is, right, it's arithmetic, and am I talking about terms or sums? I'm talking about terms. This is the formula for the nth term of an arithmetic sequence. Right, and this is the formula that I'm going to need to use here. Right, now what we know that the first term is 7. We also know that 35 is the 15th term. That means that 35 can go over here. A is 7. Remember that 35 is the 15th term, so n is 15, so this will in fact be 14 lots of d. Right, there's only one variable left here, right? If we subtract 7 from both sides, we get 28, it's 14d, and so we actually get that d equals 2, right? Now we say to ourselves, what did the question actually ask for? Well, it asked for T8. T8 is just going to be, using the same formula, it's going to be my A value of 7 plus 8 minus 1, which is 7 lots of D. Right, and I'm going to get a total of 21. Right, so the 8th term of that sequence is 21. Okay, let's look at another example. Right, remember this one is around sigma notation. Okay, and remember the trick with sigma notation is write down the first 3 terms. When x is 1, we actually get 1. When x is 2, we get 3. When x is 3, we get 7. Right, now this is not quadratic. And, sorry, this is not arithmetic. And, in fact, it is not geometric. So, Nancy and Kenga, we have a problem because we actually don't have a formula for a quadratic sequence. However, this is only asking us to find the sum of 4 terms. So what we're going to do is we're just going to complete writing it down, and we're going to just add these up in our heads, and in fact we get 24. Okay, and that's the deal there. Right. This next one says calculate this thing to 15 terms. Now, we're definitely not expected to write down all 15 and calculate them manually. So this one must be arithmetic or geometric. Okay, and we can use a calculator by all means. If we go this minus this, we don't get the same as if we go this minus this. This is not arithmetic, okay? However, if we take this term and we divide it by this term, we actually get 3/4. And it doesn't matter which term we take here, if we divide the previous term, right, we always get 3/4. So this thing is in fact a geometric progression. As soon as I write down R, I'm saying it's a geometric progression. I also know that A is 45 over 4, and I know that I'm trying to find a sum. So I'm going to use my sum formula, which looks like this. It's given to us on the formula sheet. A 1 minus R to the n over 1 minus R. And I'm going to put in all these numbers. And what I'm going to get is 45 over 4, 1 minus 3/4. Remember, I'm adding up 15 terms here, over 1 minus 3/4. All right, and I'm going to put all of that into a calculator. And in fact, what I get is 44,399. Okay, that's the sum to 15 terms of that sequence. In fact, it's that series. All right, let's have a look at the next one. Now we are told 3 terms of a geometric sequence are 6, x, and 54, and we are asked to find the value of x. Okay, well, remember, if this is a geometric series, or sequence rather, then the second term divided by the first will in fact be equal to the third divided by the second. Okay, now remember the little trick that we learned? The top of a fraction times the bottom of a fraction, top of a fraction times the bottom of a fraction. So in fact, what we know here is that x times x squared, is 324. Don't forget, when you square root, we could have plus or minus 18. All right, so there are actually 2 options. I'm going to write them down with different pens. I'm going to write a blue one. There's 6, 18, and 54. That definitely forms a geometric sequence, all right, with a common ratio of 3. Or, in the purple pen, there's 6, minus 18, and 54. That is also a geometric sequence with a common ratio of minus 3. Notice I didn't need to actually do that last step. That was just a kind of a check, just to give me a comfortable feeling that I'd got it right. Okay, now let's look at a sort of a real world kind of example where we've got to translate this into a sort of series. Okay, so Alex decides to swim and run in her exercise plan. On day 1, she swims 100 meters and runs 500 meters. Each day, she'll increase the distance she swims by 50 meters and the distance she runs by 3.5%. Okay, how far does she swim on the nth day of her exercise plan? Let's just write down a few terms. Right, on the first day, she swims 100. On the second day, she swims 50 meters further, 150 meters. On the third day, another 50 meters further. Right, so what this is asking for, it's asking for the nth term of this sequence. Now this sequence is arithmetic. So it's going to be Tn is a plus n minus 1 lots of d, right? And we know that a is 100. And we know that d is 50. If we simplify all of this, we actually get 50n plus 50. Right, and that's how far she swims on the nth day. Right. How far does she run? Well, let's write down the sequence of her running. On the first day, she runs 500 meters. Then she grows that by 3.5%. Now, to increase the number by 3.5%, we're actually going to multiply it by 1,035. 1,035, folks, is actually 103.5%. Right, so we're finding 103.5% of 500. The next day, she takes this number and grows it by 103.5%. So in other words, we're going to multiply this 1,035 in again. So in other words, it's going to be squared. All right, now this one is a geometric sequence. And remember the formula for geometric sequences, Tn is a r to the n minus 1. So for this specific one, it's going to be 500 is our a value, times by 1,035 to the n minus 1. That formula there is a formula for the nth day, the distance that she runs on the nth day. Okay, now, look at this word over here. By the time she's done 12 days, what's her total distance? Now, total suggests that we're going to need to add up, right? So we now are going to use our respective sum formulas. For the distance that she swam, we're going to use this formula because this is the sum of an arithmetic sequence, or series rather. Right. And we know we're talking about 12 days. We want the distance, the total distance after 12 days. It's going to be 12 over 2. 2 lots of A. Remember, she swims 100 meters on the first day, so it'll actually be 200. And this is going to be 11 lots of D. And remember that D is 50. Right. And what we end up with here as a total is 4,500 meters. Or we could write that as 4.5 kilometers. That's how far she swam in total. We're going to do a very similar thing with the running, but we're going to use a different formula because the running is a geometric series. And remember, the formula for the sum of n terms of a geometric series is a r to the n minus 1 over r minus 1. And so what we get on the first day, she ran 500. R is 1,035 to the 12. We're talking about the total in 12 days, minus 1 over 1,035 minus 1. Okay, and that's the total distance in 12. And that actually comes to 7,301 kilometers. Okay. Right, the next one is a sigma notation, and we know the deal with sigma notation. We just write down 3 terms to see what's going on. First term is 2/3. Remember, sigma is always about plus. Okay, it's a Greek S for sum. The next one is 2/9. And the third term, and 3 is enough, because 3 is enough to tell us what sort of thing we're dealing with, is 2/27. This is geometric, all right, with R equals 1/3. Now, 1/3 is in that magic interval between -1 and 1, so we will get convergence, and we can use this formula, this kind of special sum to infinity formula, that only applies when we've got R lying between 1 and -1, right? So in this case, our answer is going to be A is 2/3. We're going to divide that by 1 minus 1/3. Right, 1 minus 1/3 is obviously 2/3. So I actually get 2/3 over 2/3, which lo and behold is 1. Okay, let's look at this next question. Refer to this figure showing the first 3 layers of a stack of cans. There are 30 cans in the first layer, 29 in the second layer. All right, so the sequence is actually 30, then 29, then 28. All right, and the question is, how many will there be in the nth layer? Well, we just want the nth term of this arithmetic sequence. So it's going to be Tn is A plus n minus 1 lots of D. A is 30, n minus 1 lots of D, and remember D is actually minus 1. This all simplifies if we kind of take out the brackets and collect our like terms to 31 minus n. Okay, the maximum number of cans that can be stacked this way. All right, well, I think we need to realize that on the top row, we're actually just going to have 1 can, all right? So in fact, there will be 30 rows because there are 30 cans in the bottom row, right? So now we're wanting to add up, because we're wanting to actually add up 30 plus 29 in the second row plus 28 right up to the one that's on the top on its own. I think you can see that n is 30 here. I'm hoping also that you can see that this is arithmetic with a common difference of -1. And we are adding, so we're going to use our sum formula. Sn is n over 2, 2 lots of A, plus n minus 1 lots of d. All right, and what I get for the sum of 30, it's going to be 30 over 2. 2 lots of A is going to be 60, and 29 lots of minus 1. All right, again, we can pop all that into a calculator, and we get a total of 465 tons. Sorry, 465 tons. Okay. Right. Now, question 7 asks us for a formula to represent the nth term of this sequence. Okay. Well, what is it? It's growing by 2 and then by 4. This is not arithmetic. This is in fact a quadratic sequence, right? And so we are going to need to remember the various bits that are involved with a quadratic sequence. What we're going to do, here's the only formula that we get given. Tn is an squared plus bn plus c, all right? We may not even yet be convinced that it's a quadratic sequence, but I'm going to quickly show you that it is. Let's just write down the first few terms, 41, 43, 47, and 53. That's probably enough. And now underneath, I'm going to write down the first differences. And the first differences are 2, then 4, then 6. Right? Underneath those, I'm going to write down the second differences. And those second differences are constant at 2. That means that it is indeed a quadratic sequence. Now, what we need to do is we need to remind ourselves, when we've got one of these, A is given by half of the second difference, the constant second difference. And in this case, our constant second difference is 2, right? So we're going to actually get 2 over 2. We're going to actually get 1. The next thing is that this term here, the first term of our first differences, is equal to 3a plus b, right? But I already know a. I know that a is 1. So that's going to be 3 times 1 plus b. Okay? So, in fact, it's going to be, b will be minus 1. And then lastly, I also know that a plus b plus c must equal 41. Right. So what happens here, in fact, is that a, which is 1, plus b, which is minus 1, plus c must equal 41. So our general term here is Tn is n squared minus n plus 41. Right. That's the nth term of that sequence. Now, this is an interesting, just a little sort of bit of problem solving here, but it says that if we write down, if we calculate all these, the first 40 of these are all prime. Okay. Now, unfortunately, we haven't got a formula for finding prime numbers, because if we work out T41, we're clearly going to get 41 squared minus 41 plus 41, right? And this is actually 41 squared. And 41 squared is not prime, right? Because 41 squared is obviously 41 times 41, right? Which means that 41 is a factor. So it is not a prime number. Then it says determine the units digit of this term of this sequence, all right? Now, if we go and look at the sequence, the units digits follow a pattern. They go 1, 3, 7, 3, 1, 1, 3, 7, 3, 1, and so on. So they actually carry through like this. 1, then 3, then 7, then 3, and then 1. And then that cycle starts again. Right. 1, then 3, then 7, then 3, then 1. And then the next one, 1 will end in 1, then 3, then 7, then 3, then 1. Okay, now the secret here is to realize that this cycle of digits is 5 units long. So every 5th term will end in 1, right? Now, if we kind of just round this up and we looked at the 50 millionth term, right? The 50 million is a multiple of 5. So that term, the 50 millionth, will end in 1, right? So the one that is 49,999,998 is actually going to be 2 before. It's going to end in 7. Right. So our final answer is 7. Right. That's a little bit unusual, and I wouldn't necessarily worry too much about that. Okay, and that brings us to the end of that lesson.